This video we're going to discuss one of the searching algorithms called binary search. Before we start the discussion, you will see that this algorithm is something that we actually use in real life. When you are looking for a word in a dictionary or you're looking for a definition in an encyclopedia, you go to those books, if you still have a printed dictionary or a printed encyclopedia, and based on the order of the dictionary or the encyclopedia, you know pretty much where the word or the definition that you're looking for is going to be. In other words, you're relying in two facts. You're relying in your knowledge of the English alphabet. You know how words are alphabetized in order from A to Z, and also you're relying on the knowledge that given a particular word that you want to find or a particular definition that you want to find, you pretty much know based on the order of the English alphabet where to start looking for. And so you're going to see how this goes. So the steps for the binary search are as follows. The first step is you're going to take your collection, which typically is an array because we're going to need to have indexes. You find the middle element. So in an array, this is very simple because you can calculate how many elements you have on the array, divide the numbers of elements by 2, and that will tell you the index of the middle element. If you look at what I have written before, I have written a large collection of data of words all in capital letters, and of course because they are alphabetized, all the words will start with A are at the beginning, and then B, C, D, etc. Toward the middle we're going to find the words that start with M, and of course toward the end we are going to find the words that start with Z. Okay, so what we're doing is trying to figure out how many elements we have. Once you have that, you divide that by 2, and that will tell you the index of the element that is on the middle of your collection. Once you have that index, then we go to step number 2. Step number 2 simply says, okay, take a look at that at the value at that position and see whether or not that is the word or the definition that you're looking for. Of course, if there is a match, then the search will stop because we found what we're looking for. But most likely, as you know, when you look the first time, the word in the middle, the word that you're looking at on the encyclopedia or the dictionary, is not an exact match. And then you have to take a second step and decide in which direction you're going to go. So again, if there is a match, the algorithm, the technique will stop. We're done, we found it. But if there is no matches, then we need to decide which of the two halves in the collection we're going to search. What does it mean? Again, look at what we're having here and look at the example. So I have, let's say, 350,000 words. It's the normal size of a dictionary, 350,000, all in capital letters. Let's not consider lowercase words. And let's say that I'm looking for the word today. Okay, so what I'm going to do is I'm going to take my collection, which is sorted from A to Z. I'm going to look at the value in the middle of my collection, and most likely it's going to be a word that starts with M. Okay, well, that is not a match for the word that I'm looking for, which happens to be today. Okay, but now, because I know that my collection is sorted, I need to decide which of the two halves is most likely to contain the word today. Is the word today going to be in this first half? Is the word today going to be found in this half that has words that start with A up to words that start with M? Well, obviously, the answer is no. Today is not going to be in that half. Today is most likely to be on this half, because in this half we have all the words that start with M all the way through all the words that start with Z. And if I'm looking for a word like today, today is most likely to be somewhere in this section. So that's step number 4, deciding which half of the collection I'm going to search. And now that I have made this decision, I can ignore then this half. I can ignore all the words that start with A all the way to the words that start with M. Okay? Essentially, all the words that start with A through all the words that start with L, right? So What do I do now with the half that is left? I simply repeat the process. In other words, I'm going to find the middle element. I'm going to see if the middle element is a match. And if it's not, then I need to decide which half I'm going to use for my next iteration. So let me copy here what we have and reflect the decision that we have made. The decision that we have made is that now I'm going to use the second half, words that start with M, all the way through words that start with Z, and then the middle word probably will be words that start with S. And now I have a new problem, but this new problem is half of the size of my original problem. I have eliminated, okay, half of the words in my encyclopedia or my dictionary. Today is not going to be in among those words. So now, repeat the process. Go to the middle. Those are the words that start with S. Okay, of course that's not going to be a match for today. And then now I need to decide which of the two half I'm going to use next. Is today going to be in the section of words that start with M all the way through words that start with S? The answer is no. Today is likely to be in this half, words that start with S all the way through words that start with Z. And now I repeat the same process. Okay, so let me copy and paste what I have originally, but now I'm going to say, oh, now I'm going to go all the way from words that start with an S all the way through words that start with a Z. And again, by doing this, I'm going to figure out that the words in the middle is probably words that start with V. So, in this second step, one more time, I eliminated half of the data that I started with. I eliminated all the words that start with M, all the way through all the words that start with R, which precedes the S. Repeat the process one more time. Well, obviously, the word in the middle starts with V. I'm looking for today, so today is likely to be in the first half. So now what I'm going to do is I'm going to eliminate all the words between V and C. So let me copy again. Let me copy and paste. And now this time, what I'm going to do is to say, well, the words are going to be starting with S now, all the way to the words with V in that half. And obviously, what the words are going to be in the middle, I don't have too many choices, are going to be the words that start with T. So one more time, I have eliminated, by performing one comparison, half of the data that I started with. So now I'm left with all the words that start with S all the way through the words that start with V. So you can see that I'm narrowing the space where today is going to be likely to be found. And then I go and figure out what the middle element is. Okay, it's going to be some word that starts with T, and then I'm going to say, all right, today is likely to be in this second half. So I don't need all these words that start with S, so I can eliminate them. And now I'm going to say, all right, so now here I am all the words that start with T through all the words that start with V, and then here going to be the words that start with U. Okay? And then I'm going to have repeat the process. So again, these are the words that start with U. Today is likely to be in this half. So therefore, I can eliminate this half. So I'm going to do this one more time. And now I'm going to start narrowing to the words that start with T. So instead of T, I'm going to say, okay, these are all the words that start with TA something else. And because I'm going to finish here before the U, these are going to be all the words that start with TU. And here in the middle, I'm going to put all the words that perhaps start with T followed by an I. So you see now I started with all the words, 350,000 words, A through C, narrow it down to the words that start with a T, pretty much. Repeat this again, and then I'm going to say, find the value that is on the middle, right? Well, those are the words that start with TI. I'm looking for today, okay? So today is not likely to be in this first half, right? It is likely to be in this second half. All right, so eventually, if I keep doing this and I keep making what is called the space, in other words, what I'm looking at, smaller and smaller, I'm gonna get probably to a point where I have things like this. I'm gonna have the word to, as in TO, and then in the middle, I'm gonna have perhaps the word today, right? And then I'm gonna have the word toy. Last iteration of the algorithm, find the middle value. The middle value happens to be today. Does that match the word I'm looking for? Yes, I found the word, I know what it is. Now I can do whatever I need to do or discuss the definition, etc., but I'm done. Now, the other likely outcome is that I keep narrowing this space. So this space is going to be getting smaller and smaller and smaller, as you have seen. At one point, I'm going to be left with only one word. And I'm going to look at that word. And that word is either the one that I'm looking for or the one that I'm not. Remember, search has two possible outcomes. The target, the value that we're looking for, is going to be found or not. Searching doesn't guarantee success in terms of a match. So what is happening? If you have been paying attention, what is happening is that every iteration, every time that we perform the algorithm, we divide the collection into half, right? And then we discard one half. And in every iteration, we only compare the middle element. And if the middle element is not found, then we decide which of the two halves. So very interesting that this technique requires only one comparison. There is no shifting of elements. And the most important part is that in every iteration, with every comparison, we are eliminating half of the data. So again, going back to our original example, if I start with all the letters, 350,000, when I perform the first iteration, I compare the element on the middle. That is not the one that I want. Then I drop half of my data, all the words that go from A to N. So in one comparison, I eliminated 250,000 elements if I started with 500,000 elements, okay? If I started with 1,000, after one comparison, I dropped 500 elements. That's huge. That's very important because I'm eliminating data very, very fast. Let's do some analysis of what is happening. So what is happening is the following. We start with a collection that has n items that were sorted. The first iteration of the algorithm, we divide that collection, which we call n, by 2. The second iteration, we took, right, a half, and we divide that by 2. So that is equivalent to dividing the entire collection by 4. So we eliminated a half, we're left with a half. We took that half, we divided it in 2. That means now I have quarters. And then I'm going to do the next time, I'm going to divide by 2, then I have 8s. So if you notice, there is a pattern here. Every iteration, I divide my current collection by 2, exactly into 2 halves. So the first time I divide by 2, so you can think about eliminating half of the data. Okay, the next iteration eliminates an additional quarter of the data. The next iteration eliminates an additional eighth of the data. Okay, so every time that I perform an iteration, I'm going to eliminate something that is to the power of 2. Now, if I do some math, what is interesting is to find out what the value of this p will be in this equation. Okay, so let's say that I tell you, as we started today, by using 350,000 words dictionary, okay, what is the value of this p? Okay, and what does it mean? Well, p indicates the numbers of times that we have to divide our collection by 2. P means the numbers of times that we have to perform the algorithm. How many times I have to divide by 2. What it also means, and this is the important part, how many comparisons at most I have to perform to arrive to a conclusion. Okay, and if we do some math, then we see that that value of p happens to be log base 2 of n. You probably are familiar with log base 10 that you use in calculus. Well, instead of using decimals, we use powers of 2, okay? This is called a log base 2 of n. And log base 2 of n for sufficient larger values of n is a very small value, okay? It's smaller than the value of n. So we said that the expected running time of the binary search is log base 2 of n. Again, this big O is a notation, so don't worry about it. It's called big O, and it simply says that the amount of time that it's going to take to find a value using binary search on average is going to be equivalent to log 2 of n. Now, we are going to study later on other searching techniques, and you're going to see that this technique is pretty fast, and it's fast because, again, we are dividing by 2 the data that I started with. We're eliminating half of the items that we started with. So the process of finding, the process of searching move rather fast. All right, now, for you to understand what this log base 2 of n means, let's think of the following, and you can do the math. Let's assume that we start with a very small collection, an array that has 15 elements. So if in the previous equation you plugged in n with a value of 15 and calculate the logarithm of base 2 of that value, you're going to see that the numbers of iterations is 4. Okay? So if you give me 15 elements in 4 comparisons and can determine whether or not the value that you're looking for is there. Now let's double the size of the array, and let's keep that in mind. We're doubling the size of the array. Let's not get distracted by these numbers because these numbers are pretty small. So if I double the size of the array, pretty much 31, okay, and I perform the sum calculation, in other words, okay, I'm trying to calculate the value of p, right, then it's going to give me, for an n equal to 31, okay, it's going to give me a numbers of iterations 5. Okay, and then let's double again, 63, iterations increase by 1. Let's double again the size of my data, iterations increase by 1. Okay, so what I'm saying here is that as you double the size of your collection, the numbers of comparisons only increases by 1. The numbers of comparisons doesn't double or quadruple or grow exponentially. Okay? So this is very important to understand about algorithms that their expected time is log base 2 of n. As you double the size of the data, you don't double the numbers of comparisons or the numbers of iterations of the algorithm. It just simply increases by 1. That's a very powerful thing for these algorithms, which are log base 2 of n. So finally, let's do some basic analysis. Okay? The first thing that we have to realize is that you can only apply this technique if your collection is sorted. So let's think about that. A phone book is in order. A dictionary is in order. An encyclopedia is in order. In all those cases, we can apply binary search. But if you're given a random collection of values, how do you determine the value in the middle? Perhaps you could, but then how do you know in which of the two halves the value is likely to be? You don't know. So it needs to be sorted for you to be able to choose which half of the two that you're going to end up with is most likely to contain the value that you're looking for. Okay? So every iteration partitions the collections in half. Every iteration, therefore, discards half of your data. Every iteration requires only one comparison. And finally, understand not only that the expected running time is log base 2 of n, but what it means. It means that as you double the size of the data, the numbers of iterations, the numbers of comparisons only increments by 1 at a time. This is binary search, a very fast algorithm. If you haven't done so, I encourage you to watch the video on linear search, which happens to be another common technique for finding values, but is much, much slower than binary search.